Our final talk in this morning session, we have Dr. Bernard Bigot, the Director General of ITER, and this is big science for the benefit of all mankind. Please.
We hope so, we hope so. So thank you very much for inviting me to present ITER. ITER is a large international research collaboration in order to demonstrate the feasibility of hydrogen fusion. And this device is under construction in France, nearby Aix-en-Provence. On the screen you have the site as it is now, with, on the center you have what we call the Tokamak building. It will be there where we will fuse hydrogen nuclei. And in order to do that, we need a very large device. It's linked to the physics. And the main purpose is to open the way to a new, clean, safe, and nearly unlimited energy sources. Indeed, the challenge is so large that no country, whatever powerful it could be, could afford to demonstrate this alone in a reasonable time scale. It will take nearly 25 years from the very early beginning to the first, what we call full fusion power, expected to be in 2035, for this project. And so is why, indeed, 7 large members representing 35 different countries has accepted to sign a joint ITER agreement for 42 years plus 10 years if needed, and spend of the order of 20 billion euro in order to build this facility. And I'm sure you recognize all these countries. And for example, Europe, it is 28 countries, including so far UK, plus Switzerland. And we have a very good discussion, I would say, in such a way that whatever the Brexit outcome, the UK will stay in. I consider it maybe one of the biggest challenges of our civilization. As you know, no life, no social life, no economical life, no biological life without energy. The world population rely on renewable energy until the beginning of the 18th century. Just renewable energy, wind, solar, biomass and production and so. We discover the coal, we discover the oil, we discover the gas. And now the world population has grown up from 1 billion inhabitants to now nearly 8 billion. And furthermore, the standard of life has increased a lot. We use much more energy. So now we will try, certainly, to rely on renewable energy, and we want to develop them. But when you have a large part of the population which is in the cities, when you have a large part of the production means which are very intensive, massive, you need, certainly, some what we call continuous, massive production of energy. So on what we could rely? We will rely on a natural phenomena, which is the hydrogen fusion. And as maybe you know, is the most familiar way to produce energy in the universe. The stars and the sun is just powered by hydrogen fusion. It has been discovered, part from some UK fellows, part from some French one, in the early 20th century, when they consider that the sun is powered by the nuclear the fusion, hydrogen fusion energy, a nuclear phenomena, as you know, fusing hydrogen atom. The sun is of the weight of 300,000 times the mass of Earth. And at the center of the sun, under the gravitational pressure, you have a very dense plasma, 15 million degrees hot, temperature, and a density which is of the order of 100 times the density of steel. And at this density, you force the hydrogen nuclei to get closer and closer to overcome their natural repulsion at long distance and to fuse to produce helium. Clearly, it's difficult to reproduce that on Earth. So the physicist has been bright enough to imagine something different, completely different. A very low density plasma. The density of the plasma will be 1/1,000,000 the density of the atmosphere. And at this density, if you heat up the gas, the plasma, at 150 million degrees, 10 times the temperature of the core of the sun, when you collide between 2 hydrogen nuclei, they overcome their natural repulsion and they fuse with a very high efficiency. What is good is, as you see on this slide, if you collide at the 150 million degrees, which is equivalent to 0.7 million electron volt, doesn't matter, okay, the units, they fuse and they produce two new particles. One is an helium nuclei and the other one is a neutron. The helium nuclei move away with an energy which is 5 times more the energy of the collision, and the neutrons 20 times. So you have a net production of energy with these two particles moving away. Okay, as you see, 1 gram of fusion fuels is equivalent to the instantaneous burning of 8 tons of oils. Okay, the factors, the amplification factors is of the order of 1 million. How we could do that? 150 million is not so easy to put in a pot. So we do that with magnetic cages. We will use the magnetic forces. Double advantage. First, as you know, the magnetic forces could act at distance, preventing the plasma to touch, okay, the walls of the vessel. Second, I'm sure you, in this physics department, everybody knows that when you have an electrical particle nearby a magnetic line, the magnetic line will capture the electrical particles, and the electrical particle will spin around the magnetic line, continuously accelerating. So if you have a very low density and a continuous acceleration, you understand, you will reach a very high speed before you collide. It is the main reason when you need such a size. Okay, below this size, you will have some events of fusion, but so little that indeed you have to spend more energy to feed the plasma than you will get from the plasma. So it will be the first time in the world that we will be able to produce a net, okay, quantity of energy from a plasma. So it is the basics. The good point is indeed you use quite small quantity of raw material. The raw material is water, okay, in order to split the water in hydrogen, okay, and oxygen, and you will separate among the isotopes, the brands of hydrogen, the most valuable one for fusion, which is the deuterium. And for the tritium, as you know, the tritium is not a natural product. Okay, you have to use some sources, and the sources is lithium. Okay, when you collide lithium with the neutrons, and we got the neutrons from the plasma, you produce lithium. So the basic equation is deuterium plus lithium plus the neutrons, and you produce, okay, heliums plus heat. So it's exactly what's happened, and as you see yourself, even if you are very keen to save energy, it's enough resources in a half bath tube, and in the small lithium pills you have in your computer, for example. So it is with this big advantage, as shown here, that the 35 different countries, the 7 partners, agree to move on. The big advantage, it is a new source of massive energy, predictable and potentially continuous or variable power complementary of the renewable energy. As you know, the drawback of renewable energy is diffuseness. You need a large of space, and second is intermittency. Here it is massive, and okay, it could be continuous, okay, without, and you could switch on and switch out. So you could have a follow-up of the needs if you have a large amount of energy. Second, it is intrinsically safe. Why? Because you inject 2 grams of this huge vessel. The vessel volume is more than 1,000 cubic meter, and you will make a discharge. And if anything goes wrong, immediately the reaction stops in. There is no storage of energy, just a big flux of energy. So no risk. The worst case would be a fire, okay, but okay, it does not mean so much. Second, we just release helium, so no impact on the climate, no impact on the environment due to the outcome of the reaction, the fusion reaction. Last but not the least, as I mentioned, we have enough supply of fuel for millions of years for the world population of 8 billion or even 10 billion. there is a limitation, as you saw. We will produce a small quantity of radioactive material. We will have to take care, but the quantity is very small, and after 100 years, maybe the decay will come back to the natural radioactive rates. So it looks like a dream, and why during the last 60 years a constant progress has been developed. You see, you could have a tokamak which is as small as this table. If you go to the Charles University in Praha, the first tokamak ever built in the world has been gifted by the Russian indeed to the Czechies. And you could go, and with your computer, you could even have it working in order to have a fusion event. But one event, not enough in order to produce a new. So the largest indeed tokamak so far, which is a Russian word, which means torus magnetic cages, is a jet nearby here, as you know, at Coil. It has a world record, and you see the Joint European Tourist is with its all events so far, and it is expected this year and maybe in 2021 to again have a tritium deuterium campaign demonstrating again the feasibility of the hydrogen fusion. Unfortunately, the Joint European Tourist, the size is limited, and there is no chance to have what we call a burning plasma, which means a plasma which will be self-sustained and producing energy. So it is a recent image of a plasma jet. As you see, it's irradiating a lot. Here is a famous vessel with a wall, you see, and collecting the energy on what we call the derivator, which is a piece at the bottom of the screen, and it fade up, and maybe it could start again and again. So the UK has been always very strong in hydrogen fusion. For example, in 1934, the first man-produced small-scale fusion reaction has been done indeed by Hans Rutherford in his team. I don't know where it is, Cambridge. No, so anyhow, I don't want to go through, but in 1997, the Joint European Tourist has been completed, and they operate, and presently it is the largest tokamak in operation in the world, and you expect maybe to be closed, maybe in 2024, 2025 at least, and so is why ITER has to take over. How it started? Indeed, it started in 1985 when these two gentlemen, I guess you recognize their face, decide that it was enough to go for the preparation of nuclear war, and they have to recycle in some way the physicists. And they request their physicists to try to demonstrate the feasibility of hydrogen fusion for peaceful purpose. Immediately indeed, they set up a large international program with 3 laboratories, one in San Diego in the US, the other one in Europe, nearby München, and the other one in Naka in Japan, in order to be able to demonstrate and define the way it is possible to fuse hydrogen in good condition. During 20 years nearly, they have developed the design, and indeed in June 2005, the 7 members, and you see their names there, have agreed, indeed at Moscow, unanimously to build ITER and decide to go on the site proposed by Europe. And 1 year nearly later, they signed the agreement, and now, altogether, they are committed to deliver. And altogether, they represent more than the 50% of the world population and about 85% of the global GDP. We could not expect to be much given. It's quite complicated, indeed, the way they organize the governance. Because all these 7 countries believe that if fusion is successful, it will be a real breakthrough. It could change the whole world energy supply picture, and they want to prepare their best world industrial company to deliver the various components. A lot of innovation is needed, and so they decide to have a central organization, I am just adding now, and 7 domestic agencies, as we call, to procure in kind the various components. It's like if you consider to build a car and you decide, you will have 35 different countries, each of them in charge to manufacture one component under the design of the central organization. Quite challenging indeed from the point of view of management. Okay, in the ITER joint agreement, the breakdown, the sharing of the various components has been decided very precisely. It has been agreed that the non-European countries will contribute with an equivalent value of 9% and Europe 45%. Why 45% for Europe? Is because it is in Europe, and as you know, there will be much more benefit for economics if it is in Europe elsewhere. Here is a design of the tokamak. Indeed, you have a big box. Okay, the big box is 30 meter high, 30 meter diameter. Is a cryostat. Why? Because inside it will be helium gas at minus 190 degrees centigrade. Okay, in order to preserve the energy. Why? Because the magnetic cage is made of superconducting coils at minus 270 degrees. The coil are just around what we call the vacuum vessel. The vacuum vessel here is the piece which is in orange, is like a torus, 1,800 cubic meter. And inside you will have the plasma with 800 cubic meter of plasma. So you see, at the center of the vacuum vessel, you will have a tube which will be the volume of the plasma, contained by the magnetic cages. Okay? A few meters away, you will have water collecting the heat. How we collect the energy? I explained to you that the neutrons will be produced with a speed 10, which is an energy which is of the order 20 times. The neutron is not influenced by the magnetic cages. It will escape. It will escape and it will hit the wall of the vacuum vessel like a bullet on a steel plate. It will be abruptly stopped, and so it will transfer its kinetic energy to heat. And so the vessel is a double wall where the water will flow. You will heat up the water at around 200 degrees. You will produce a steam, and as you know, since Carnot principle, with steam you could make works and make the turbine producing electricity. It's exactly what's happened. The challenge is you have to assemble all these pieces with a very strict precision. For example, the magnetic axis of the magnetic cage, as we'll show you in a few minutes, has to be positioned with regards to the axis of the vacuum vessel with a precision of 0.5 millimeter, while the size is 20 meter. Very challenging. And you see, all these pieces are weighing nearly 23,000 tons. And as I heard, we are working in France, we take the comparison with the Eiffel Tower. You see, it's a lot of pieces of steel there. Size matter, as I explained to you. The world record now is at the jet. The volume of the plasma is 80 cubic meter. In ITER, it will be 10 times more. In the jet, you feed the plasma with 23 megawatt of power, and you get 16. The yield is no more than 70%. In the ITER, we will double the heating power, but we will multiply by 30 the fusion energy. Very large enhancement on this. So the ITER mission is clearly to demonstrate the feasibility of technological fusion, of hydrogen fusion for peaceful purpose, with a goal to demonstrate that the fusion power will be 10 times larger than the heating power in the plasma. Clearly, we need some more energy for the pump, for all these things. And the long-term expectation is to go up to 40 times. There is no limit from the physics to go with this. How it works, as I explained to you, you pump out all the gas which are in the vacuum vessel chamber, because you don't want that the hydrogen collide with some other atoms, because it is not at all efficient for fusion. So you pump out all the gas. When you have the proper low gas density, the high vacuum, you inject 2 grams, and you will make an electrical discharge. Since the vacuum vessel is embedded within the magnetic cage, immediately, okay, the nuclei will be accelerated. You will produce a plasma which could be up to 15 million amperes, and with the Joule effect, as in any electrical cable, you will start rising the temperature, but not sufficiently to get the 150 million degrees. So you need some extra heating with some electromagnetic waves, some high energy neutral particles, and as soon as you get the 150 degrees, it starts and it runs burning with just a small amount of energy in order to maintain. The key point is the magnetic cages. It will be the largest ever built magnetic cages, made of 8 vertical coils, what we call toroidal field coils, and 6 horizontal wall polarial field coils. And you are just waving a magnetic cage like the threads of my jacket, and very precisely. Otherwise, the particle will escape. So the big challenge, and you see the size of the fellow compared to the size of the cage. The cage is as high as a 7th floor building. You see? And as I explained to you, you need to assemble all these pieces with a precision which is below millimeter. Big challenge, clearly. So, for example, it is an image of what will happen. You have at the center, the tokamak with all the feeders, in order to feed the superconducting. And you see it's represent nearly 10,000 tons, and we need to cool down all these things, at minus 269 degrees to be precise. The challenge is we are manufacturing component. We are more familiar in a shipyard, but with a precision like a watch. For example, these pictures show a few weeks ago, indeed, the first success to assemble the different pieces of the toroidal field coils. The coils are made of superconducting materials. I'm sure you are aware it is ceramics. Ceramics is very fragile. So if you have the huge magnetic forces directly under the coils, the cables, you will break apart. So you put them in casing indeed, and the 2 pieces of the casing, each of them is 150 tons, 20 meters long, has to fit with a precision of 0.2 millimeter. And indeed, I am pleased to say we succeed. A few days ago, I was in Japan just to make the fabrication acceptance test, and we are complete as well. Another coil has been manufactured indeed last week in Italy, nearby Venezia. The project started in 2007, indeed, as I said, we signed in 2006, and at the beginning it was a very low start, a lot of difficulty, because the project management was not suited. People feel that it has to be like at the UN, consensus. Nothing is moved as long as there is no consensus. It could not work, certainly, in this case. So they call upon me, and I say, I am not a miracle man. I just want you to accept the recipe. And the recipe is simple. First, you have to empower to take any technical decision the Director General. If you are not pleased with his decision, fire him. But as long as he is in charge, you have not to contest any of his decisions. Second, to work in the most integrated way. And third, to have a very reliable, even if it is a challenging schedule. So when I came in, indeed, you see the work site was quite nice. It was like a flat, games, And 5 years later, we are a little bit more advanced. We have a very precise schedule. As you see, all the main components, I spoke about the vacuum vessel sectors. We have breakdown the torus in 9 pieces, coming from Korea, coming from Italy, coming from India. All these pieces will come on site and will be assembled. As you see, they are supposed to arrive this spring. The coils also, we will assemble of that, and we expect to have what we call the first plasma by 2025. Big challenge, no float. Second, once we have finished the first plasma, which will be only a demonstration that all the pieces has been properly assembled, we will have to equip the facility with some further equipment. For example, the wall, the first wall, has to be equipped with tiles. Okay, there is 440 tiles. Each tile with its support, each of them are individually cooled, because you have to think about that the flux of energy is absolutely huge. It's of the order of 5 to 20 megawatt per square meter, which means like if you have 20,000 individual heating small devices on a square meter. And so you need to have a system in order to move away all this very large flux of energy. And these tiles, it could be installed only with the robots. And so it takes time with the robots to be able to connect each tile with the pipe and all these things. We could not do less. So once we will have the first plasma testing successful and the tile installed, we will start to do real physics. It will be end of 2028. We will have a first plasma, not with deuterium-tritium, but with deuterium-deuterium. Okay? 18 months we will offer to the physicists to play with our devices and learn how to move on. Next, we will install some extra heating. And again, in 2032, we will offer to the physicists opportunity to demonstrate how the system works well. And last but not the least, we need to continuously recycling the fuel. Because when I inject 2 grams of hydrogen, before the plasma will stop, if I don't sort out the helium, is very short. So 1% of the injected fuel will fuse, and I have to separate the 1% helium produced for the remaining part, and so to recycle all. So it will be the largest, for example, recycling hydrogen separation plant in the world. I am pleased to inform you that we are serious about our commitment. Since 4 years, we are on track. Now, at the end of 2019, 67% of the activities to be performed from early design to first plasma has been completed. Indeed, since 4 years, the current monthly progression rate is of the order of 0.7. I'm sure you are knowledgeable that up to 2025 is 70 months to go. 70 multiplied by 0.7, we are able to complete the 33% there. However, as everybody knows, the challenge is assembling. Now we have the piece which have been manufactured according to our expectation, but when you assemble some piece like this with a very high precision, it's challenging. So it's good to have some float, but not so many indeed. So it is a recent picture on the side. The work site is as it is. I'm sure you understand now in the center. You have this Tokamak building. Behind you have the assembling hall. We have to pre-assemble the component, because we will position the component in a huge cylinder, what we call a bioshield cylinder. Why? It's because even we will produce billion of neutrons per second. We will capture 99.999% of them, but the very low percentage represents still quite a large quantity. And these very fast neutrons has to be collected and not escape to the environment for the safety of the workers and the environment. And so you have to put all the big components from the roof, like you put candies in a box. But each candies is weighing between 500 tons and 1,500 tons, and you have to position them with the precision of millimeter, as I explained to you. So is why we need this assembling hall. And all around we have different components. For example, we have a switch yard, which will be able to power, for example, a city of 3.5 million of inhabitants, but we need it on 10th of a second when we start the plasma. But we need it. It is connected to the European grid. Second, we need to convert the AC power to DC power. The coil has to be fed with DC power. It will be the largest converting system in the world. 70,000 amperes has to be converted. And last but not the least, we will produce a large amount of heat. So we need to cool down the system, and is why we have what we call the heat rejection system, which has been designed. So to complete my presentation, just a few slides of where we are. Indeed, as you see, the assembly hall is finished, is qualified, it is operating now. and I will see some picture, I show you some picture. But we have now to finish the coverage of the Tokamak building. The civil works has been done, and now we have to do in order for the big cranes able to lift the pieces and position them. And this picture indeed as 2 weeks ago, and yesterday when I left the site, it was near complete. It is supposed to be fully completed by the end of March and operationally qualified. Okay, you see the second part of the slide on your right. It is what we call the Tokamak Pit. Okay, the famous bioshield wall with the crown where you will sit the cryostat and all the tokamak. It is ready. Okay, we will position them, and you see there is a lot of window. It's a second paradox of the heater. Okay, we need to confine the plasma very strictly, but we need a lot of opening in order to have the water calling in, okay, cold water, hot water out, to have the robots able to manage, okay, the different equipment. There is 280 penetration, what we call penetration windows, in order to be able to connect with the vacuum vessel. And I'm pleased to say it is ready. Here you have the assembling hall. You see the big cranes from the top. Okay, it's two cranes, beam, able to lift 750 tons jointly, and they will lift the piece up to 30 meters above the ground and put them, as I said, as candy in the box. And we have made some mock-up in steel, in concrete. The mock-up are representing the coils, because we need to train the operators. The coils, it lasts more than 6 years to produce a coil. I don't want the operator just, okay, on his early training to make it, okay, falling apart. So we have to qualify the people. Okay, the cryo plant, I need to produce a huge amount of liquid helium. 25 tons of liquid helium will circulate, okay, constantly within the coils. And so it is okay, nearly completed. It is supposed to be commissioned, okay, this fall. The heat rejection system also, it's quite new innovative technologies. We will make the water, the steam indeed, as hot water, okay, moving in a swimming pool indeed, a large one. In such a way you have to reduce the size of the cooling tower. Very innovative. The cryostat workshop is like a can, the biggest can in the world. Okay, it's 30-meter diameters, 30-meter high. Each part is weighing nearly 1,000, okay, 200 to 300 tons, and very high precision. And I'm pleased to say we have finished a base. The base will be positioned in the Tokamak Pit early April. Okay, we have a lower cylinder, okay, and an upper cylinder. The lower cylinder is indeed already outside of the workshop. It is this large, okay, white, okay, foils. We have put it away. Okay, and it is now under temperature and humidity control, and it will be put, and we will have to weld these two circles, 30-meter diameters, 5 centimeters thick, with a precision of half a centimeter, and helium leak proof. Big challenge for the industry, clearly. Okay, so we are moving on, and the PF coil winding, we have indeed 6 horizontal coils, what we call the poloidal field coil. The smallest one, less than 10-meter diameter, one is made of in Russia and the other one in China. And the Chinese one is supposed to arrive before June. Okay, and the largest one, 24 meters diameters, 17-meter diameters, has to be built on site because they are so large you could not expect to transport them. And we are moving correctly, and each of these is of the order of 400 tons and to be positioned very precisely. So just a reminder, a breakdown of the various components, and you see the complexity to manage all these different stakeholders. And a very important point is even if every members with their suppliers are delivering the component, all the intellectual, industrial know-how, okay, properties will be shared among the 35 different countries without, okay, any limitation. It is a condition. So, just I try to convince that not only on the work site progress are real, but also on every site in the members. For example, we are just finishing the 400 tons, okay, ring-shaped coils in China, indeed under the supervision of Europe. Europe is moving on in producing the vacuum vessel sectors, in charge. India has finished the top lead of the cryostat. It will arrive in a very few weeks now, and we will have to assemble this piece. And as I mentioned to you, the coils, the first one has been finished, and very recently I went to Japan to see. I'm sure you understand, you see the size of the group of people in the middle, and it is enough to accommodate all this thing. It is perfectly fitting with the precision of 0.2 millimeter everywhere. Very big challenge, finishing the first vacuum vessel sectors. In Korea, I expect it will be finished in the very next week. You have to assemble pieces which are weighing up to 150 tons together with a geometrical requirement of the order of millimeter. Russia, the second coil, the American, which are finishing the central solenoid. We have very good collaboration indeed with the jet, for long, because it is the closest devices in the world so far, and so ongoing many cooperation like this, and I am very pleased to see that it's worked fine. I try to convince it's real picture. It's not color picture. It is Provence picture. In the early morning indeed, and so we are ready for assembly. All these components, you see the first polyidal coil from Europe and China, vacuum vessel sectors, will arrive during these next few months. The works for the building are well advanced and we are online. So really ITER is moving forward. So thank you very much for your kind attention.
Thank you very much. And for, I think, what we've heard so far in the morning has been big science, but it's often been slow science. It's science that takes many decades to come to fruition. And it's been very striking that you've given us the sense of urgency and that things are happening right now. So that is very, very striking to hear. I'm going to throw the floor straight open to questions. There's certainly one here, and then we'll take that. Oh, well, we'll take that one first.
Sorry, me first. Thank you very much for this. It's really fascinating. You must be probably the best project manager in the world. And the question is, can you please come and run our railways? Because this is a small challenge in comparison. But now for real question. So I once had the privilege of listening to the gentleman who runs JET. And he passed this in standard fusion sort of science industry joke that goes something like fusion energy is 30 years away and always will be. And obviously that got the laughs. But watching your presentation kind of makes me feel like, wow, it's kind of near imminent, at least when the science and research is concerned. So my question is, given that there is such good progress of this project, what is the thinking in respect of how, once this is working and once we have fusion as a viable proposition, how is it going to actually translate into the reality of delivering this near limitless energy to the world? Because obviously what is going to be... So CERN deals in fundamental research and publishes freely. ITER is going to publish freely the intellectual property, but what about the idea of scaling it across the world? How many of these do we need to fulfill the energy needs of the world? And also on a more practical level, how are we going to plug it into our existing energy grids? As we know, 40% or something of energy is lost in transmission. So what is the thinking around sort of, dealing with that? Sorry, long round question, but...
Okay, a lot of good questions. As you know, they are very often addressed. So clearly we have a roadmap in some way. And again, your comment about fusion is a promise for the next 30 years as always. Indeed, so far, people didn't realize that you need a size. Below this size, it will not produce energy. There is some alternate technology, but with the Tokamak, without this larger size, it is difficult. And as I explained to you, the investment will represent more than 20 billion. The best company in the world take 6 years, for example, to design and manufacture the vacuum vessel sectors. 6 years in order to design and manufacture the coils and all these things. So before it was like a dream, but we are not considering properly the input in order to make this dream true. Now, my conviction is that these 7 large partners, 35 different countries, provide the resources to make the demonstration real. Now, what is the roadmap? The roadmap is the following. 2025, first plasma. If we succeed, from my point of view, I am very confident that we will move to the end of demonstration. As I explained to you, we need a stage approach due to the limitation of resources. You have to be clear, and also the challenge of some of the most complicated, for example, the neutral beam injectors. Which will be 40 amperes. 1 MeV, 1 million electron volt, has never been done before. We have now a mock-up in Italy, in Padua, where all the members have assembled the different components to make the testing. So it takes time to finish and demonstrate with high quality what we are doing. 2035, my expectation is to have the first what we call full fusion power experience, producing 10 times more heat that you feed in. It could not be shorter. To be frank with you, it's a long journey to demonstrate with high quality and reliability the phenomena. After that, the expectation is the following: to work jointly, with all the scientists, fusion community in the world, to play with the different parameters in such a way that 5 years later we will know enough to give credibility to this technology for energy production. Now we will produce energy but not connected to the grid. So by the years 2040, 2032 maybe, at most, I guess the utilities will consider, if we succeed, that it is a way to substitute to the fossil fuel and maybe to the fission nuclear energy. Why? Because these two sources of energy have the drawback, or they are exhausting. So working jointly with renewable energy to demonstrate that it is a way to get massive, clean energy. It will take 10 years, is my expectation, 10, 12 years for the industry to be able to have industrial design, to have, scaling up all these things, selected among the various choices. Because around the heater, we have many different heating systems, we have many, diagnostic, all these things to know more. It is a research project. So my expectation, to make it clear and short, by to the year 2055, 2060 at most, we should have what we call tokamak devices connected to a national grid. To be frank with you, I see now China trying to ramp more fastly. They expect to start even by 2040 in order to build their first devices, and so it will be maybe in 2050 that the Chinese will be connected. Now you come to the question, how many of these devices will be needed? I explained to you that we will produce a huge amount of energy, but it will not feed with a single device the whole world. It will make no sense. There is a limitation of the material to sustain the energy flux. You will need maybe 400 or 500 of these devices in the world to substitute for the whole energy as it is now. It is the order. The good point, it could be a big investment, but as you know, I don't speak about the pumping the helium and so. The vacuum vessel and so, there is no mechanical move. So we could expect that the civil works and the vacuum vessel could last for 100 years. So it's big investment, but indeed the operational cost will be limited. So it is the way we are working. It's my perception. Now we rely 80% on fossil fuel. Everybody know, it is an intermediate storage of sun. This storage, we are exhausting it, and we are spoiling the environment and spoiling the climate. We need an alternate option. For my physics background, I see no other option to go with this hydrogen fusion, which has been demonstrated in the stars and the sun for billions of years. Okay, so it's a natural phenomenon. Are we bright enough in order to be able to use this natural phenomena to produce sustainable energy? Is my challenge. Is your challenge also, altogether.
Thank you. Okay,
this question follows on from the previous question. How much bigger than ITER would a working power plant be? Or would it be the same size or 10 times the size? Or?
No, it will be at maximum double size. Maximum double size. Okay. There is some improvement. For example, we are using a superconducting material which has been heavily used, for example, at the CERN. This material is not maybe the most advanced one because, it takes 30 years in order to qualify this type of materials. So I expect that in parallel to the ITER progress, the physicists, the industrial will make maybe more efficient coils, more powerful one. And so, for example, if I double the capacity of the coils in terms of magnetic field, I divide by 4 the size. So now I will produce nearly 500 thermal watt. I expect to have a capacity to go 10 times larger.
Sorry,
thank you very much. I have some questions around the intellectual property. I understand this is a research project and you've made agreements that, you know what you want to achieve, and the contributors contribute freely to ITER, the technology they develop along the way. But some of these technologies are actually, components of it, parts of it are not brand new technology, but existing technology that may have been patented in the past already.
Yes.
And, once a working demonstration unit works, there will obviously be further perfections, and those further perfections would then not necessarily be part of ITER itself, but would be, developed, might be patented by whoever does that development. So I'd like to kind of understand the whole situation of intellectual property around ITER. What came before, what is in there now, what will go in there, and what might be developed afterwards. How will this work?
It works within the ITER agreement. It is a special provision on intellectual property. It is explained that there will be what we call background intellectual properties, something which is already known from the companies, and the companies are owners of this property. They have to record this background intellectual property and make it available. Is part of the agreement. It has been the agreement. Okay, you could not prevent somebody to use your background intellectual property if you want to go with a fusion power. And we have the generated GIP intellectual property. All these are precisely recorded. As I explained to you, the scale of the demonstration is decades. So the people which know now, maybe in 3 decades from now, they will not be there to explain in detail what they have done. So we need to record very precisely this. It is a rule. If you have developed something which is usable for other purpose, clearly it's the property of the company, and he has right to develop this other device. Indeed, there is already. We have, for example, qualified the coils material, the superconducting coils. It has never been done before. We have produced at the industrial scale of the order of 1,200 tons of superconducting material, which is titanium, niobium, and niobium titanium and niobium tin. Now the medical industry of the magnetic recording, ERM, some companies have now decided to go with this new material, based on the new way to produce this material, and they are developing improved, and so they have to pay some royalties to the others. So this is the basis of the agreement. Intellectual property and know-how is shared among all the members.
Thank you. Question over here next.
Sorry. Yes. So for the next step, I'm just wondering, how specialised is the operation of ITER going to be? Because if you suddenly have 400 of these that you want to build, then you need to have the people who know how to run them.
Yes.
If you see what I mean.
Yes.
So how specialised is the operation? Can you train the next? Can you actually get enough people into the control room to train the next generation?
Okay. Clearly, we need to prepare the next steps. So when I arrive, I have defined two networks. The first network is the ITER Scientist Fellow networks. All over the world, in the 35 different countries, we are building a network of scientists which are thinking about what will be the best operation condition in order to demonstrate, for example, the sustainability of the plasma, how we could reduce the feeding power and all these things. And we have a second network, which is a ITER Operation Fellow network, where people in all the smallest tokamak in the world, the JET, but also the K-Star in Korea, the D3D in San Diego in the US, the ASDEX in Germany, all these are now be prepared. And I am ready to hire some of these people, preferentially people which are young, because as you know, in 2035, when we will full fusion power, is still 15 years ago to go. And so we need to prepare all this new generation to operate. We are starting with this large program. And the main purpose of this ITER project is to train people, to build expertise and competence in order to manage this large amount of it. Everything will be remotely controlled, as you could understand. But we define and we have simulators, for example, to demonstrate how we will operate.
Thank you.
Is basic research, is a fundamental research. At the same time, it is industrial scaling approach.
So we're running out of time, but not out of questions. There is one at the back. I know there's one down here, and there was one over there. So we'll just, if we could make this as quick as possible, then that would be very, very great. Thank you.
Because this project is taking place over such a long time period, do you have any concerns that it may be made defunct by a new, more advanced technology before it's completed?
Yes, certainly. During the lifetime of the ITER project, new technology will be developed. But you know, if you just wait after always the new technology, we will never move. When you start operating any devices, you learn. And so we will learn, including how we integrate the new technologies. It could be a breakthrough. Again, as maybe you know, quite a larger number of small spin-off has been devices, and so some rich people now give some hundred of millions of dollars to explore some of the technologies. As maybe you are aware, there is a company which is a General Fusion. We try to do it with engine pressure, with pistons, like this. Good. If they succeed, I would be so pleased. If I push them to run off, it will be so good. But so far, with my physicist understanding, I see no easy other alternate in order to produce energy. Don't forget, for example, these people could do at very scale. As I spoke to you, you could have a tokamak on the table. It's not a big deal, You will have very few neutrons, so you put them in a room, you escape a little bit, it's fine. But when I will produce billions of neutrons per second, no way. You need to have a strong, nuclear protection safety strategy. So good. If anybody succeeds faster than me, I will be delighted.
Thank you. Thank you again.